Evening and welcome to the last in our series of the West Midlands Chemistry Teacher Centre Sixth Form Lectures. And this evening we are delighted to welcome Dr. Tom Smith, who's the Managing Director of Carndu Limited. And he's worked in the explosives industry for over 35 years, providing consultancy services, expert witness, and also training. Tom also lectures on many aspects of pyrotechnic chemistry and firework displays, design, and safety. And although November the 5th has passed, we're delighted to welcome Tom to talk tonight about fireworks. So without further ado, I'd like to welcome Dr. Tom Smith.
It's a slightly changed talk, as you can imagine, because I can't stand in front of you and light things and fill the lecture theatre with smoke, but I've recorded some of the practical demonstrations, so I hope you'll find it entertaining, find it interesting, and look at firework displays in a whole new light. As Mark says, this has been an odd year. November the 5th has been and gone without very many firework displays actually happening, but life still goes on and the work still goes on, and we're planning hopefully for something good in 2021. Let me tell you a little bit about me. I'm a chemist, an organic chemist. I was at Oxford in 79 to 85, as you can see there. I've worked all over the world now doing displays, but also as a consultant to some of the larger events around the world where all the other aspects of putting on a display become important, increasingly so actually, and I'll tell you a little bit about that in a moment. I've done an expert witness work, I'm chairman of various groups, and I'm obliged to tell you that I've written a book, so you should all go out and buy that, of course. Fireworks, well, there's a lot of really good science there, and I'm going to concentrate on the chemistry tonight. So compositions, rates of reactions, effective particle size to an extent, and tell you a little bit in sort of three parts what the chemistry of fireworks is. The basic chemistry, how we turn that chemistry into fireworks, and then how we turn those fireworks into a display. But there's lots of other good science there as well, particularly now things like the ballistics. What goes up must come down, and we want to know exactly where it's going to come down for safety reasons and for planning a good show. Increasingly, of course, environmental chemistry, and you may have read all sorts of stories about how polluting firework displays are. In fact, actually, they're not very polluting at all. Just as an example, the London New Year's Eve show of previous years, the amount of nitrogen oxides and sulfur oxides released to the atmosphere from the display was about 1/300th of that from the people coming to the display in cars and trains and the tube and everything else. Now, of course, as soon as you say that, somebody says, well, if you didn't have the display at all, we wouldn't have 301's worth of pollution. But that's not real life. We still need to be entertained, and probably this year has taught us even more than ever that we need to be entertained. And then meteorology, a knowledge of what's going to happen with the weather during the displays, and of course, risk management from everything, from manufacturing to transporting to using to disposing. Okay, there are some buts though, and the buts are that fireworks are explosives, and the explosive industry is very highly regulated, full of acronyms and things. But actually in the UK, it's illegal either to manufacture or break down fireworks without a license from HSE. So don't take what I'm doing and go and try it yourself. And absolutely, as the bottom line say, a little knowledge is a very dangerous thing. Certain chemicals are completely incompatible with one another. And if you mix them, you can end up with a terrible mess and an explosion, and its effects on the body are horrendous. So let's think about a few of those precautions. Well, sensitivity is the first one. What we're making are explosives. They are high energy materials, and therefore you don't want to initiate them accidentally. And the measure of how accidentally they may ignite is their sensitivity. I'll show you a little bit about that in a second. They're made of heavy metals in many cases, so there are toxicity effects. They're hot. Nearly every firework burns hot, somewhere between 1700 degrees and 2500 degrees centigrade. So if you're close to them or you're affected by them, the burns can be severe. And of course, they'll have chemicals in the burn wound as well. And of course, they're explosives. At the close scale, fragments that are hitting a body; at large scale, completely destructive. So let me just show you a little bit about sensitivity. Here is a very short video with a couple of mixtures. First is quite a significant amount of mixture. Here we go. It's, as you'll see on the screen, ammonium nitrate and zinc. And we're going to add a little bit of water to that. And nothing seems to happen. And gradually there will be a reaction between those components. And it gets to the point at which actually the gases that are being produced ignite. But it was a relatively slow start to that, but the consequences of it, high temperature flame. But here's another extreme. This is silver nitrate and magnesium. If you look in this little white pot, there's a tiny amount of composition at the bottom, just that little speck of brown at the bottom. And this time, instead of adding liquid water as a droplet, we'll add it as a spray, slightly remotely. And the reaction is instantaneous and violent. And that's the thing, obviously, that we try to avoid with any of the chemical mixtures that we're producing. Is something that is so unstable that it can go off accidentally. And it doesn't take very much. This is an experiment done years ago to look at the effects on a human if a composition ignited. So just for relatively small amounts of black powder, even 100 grams, would produce a fireball that totally encompassed anybody who was working at the bench. And if you're totally encompassed, you're going to get severe burns, and possibly even leading to fatality. So it's not things to be trifled with. These are explosive compounds. They have to be treated with the respect that they deserve. At the far end, then, when you have a lot of fireworks together, things can go very badly wrong. So here's a 20-foot container with 5.5 tons of 75mm shells, and we'll talk about what they are later. And the camera, as you see, is quite a long way away. There's a container there. It'll be lit remotely. Doors burst open. And you get this mass effect of all those shells. And they're still going off now, but the whole lot was ejected out of the container and then subsequently lit on the ground. And it gets even more extreme. Here's a 20-foot container with waterfall sticks, which are a relatively benign firework. They produce just a shower of silver sparks, the sort of thing you might see lit at Edinburgh Castle during Hogmanay and New Year's celebrations. But this time 8 tons. We're rather farther away from the container this time, but just look what happens. The whole lot consumed almost instantaneously, acting exactly the same as a high explosive charge would. So let's think about the pyrotechnic chemistry. Well, I'm going to talk about some different topics here, some very simple compositions. What is the basics of what we call a composition? If you like, that's a recipe for a particular mix to produce something that is making stars, colors, glitter, whatever it might be. A little bit about black powder, a little bit about color, because that's the essence of a modern firework display, is what goes into the color compositions to make all the effects you see in the sky. A little bit about spark splitter and strobe, and then a touch about noise producers. Well, all firework compositions, all pyrotechnic compositions, are basically 2 components plus other things. The 2 basic components are oxidants and fuels. And the basic chemical reaction that's going on is an oxidant and fuel to give products and heat. And then other things added to that mixture will produce the colors or produce the noise or will produce the sparks. But the basic chemical reaction that's going on is as you see it on the screen now. And that makes it different from, for instance, burning a match in air, where the atmospheric oxygen is the oxidant these firework compositions have the oxidant built into them. And that means you can't put them out. Once they've started to burn, they will burn all the way to completion, and they'll burn really hot. As I said earlier, 1700 to 2500 degrees is not atypical. And trying to put it out by pouring some water on it will make no difference whatsoever. In fact, most of these compositions will intentionally burn underwater, so no atmospheric oxygen. Things like distress flares. You want them to be able to work in any conditions, including the most horrendous conditions at sea. So what are the oxidants? Well, the most typical ones are the ones at the top: potassium nitrate, perchlorate, and barium nitrate. Ones at the bottom are very good producers of the effects that we want, but all of those three, potassium chlorate, ammonium perchlorate, and ammonium nitrate, have problems associated with them, as I sort of alluded to earlier. You think that potassium chlorate would be a perfect oxidant to be able to produce fireworks with, but what it does is to produce very sensitive compositions. In fact, in the UK, it is illegal to mix compositions that contain both potassium chlorate and sulfur. And that goes to the extent of having a factory divided into two: one half that deals with sulfur, one half that deals with the very strong oxidants, particularly potassium chlorate. And nothing must go between the two. Not people, not tools, not clothing, nothing. The fuels are the most typical of sulfur and charcoal. They're the fuels that are involved in black powder. But increasingly metals are used as fuels, so magnesium, aluminium, magnesium and titanium, both of which sort of arose from the aircraft industry. They're lightweight, non-oxidizable metals that produce very bright white colors. And then sometimes we actually want to slow the reaction down a bit so that it doesn't happen too quickly. You don't want a star from a shell in the sky burning too quickly, because it doesn't make a good firework. You want to see it hang there in the sky. So we might add wood meal or resins, which have a dual purpose to act as both a fuel and a binder, in order to slow that chemical reaction down. Then there are all these different additional components you could add to the mixture. So to make sparks, you add actual metal powders. Just like an angle grinder on a piece of iron produces goldy sparks, we can add metallic iron to a mixture and use the temperature of the pyrochemical reaction, that oxidant and fuel gives product and heat, to ignite those sparks and to make them glow in the air. For colors, we don't use metals, but metal salts, and I'll come back to that in a moment. And then we can add things like chlorine donors to enhance that color production, because it's not metal species in the flame that are producing the color, but actually metal, normally chlorine species. Not the thing you can buy in a bottle, but a high temperature species like a metal chlorine sort of dimer type of thing. And then we can add other things: delay agents for glitter effects, items that we use in order to help the manufacturing, so buffers to prevent corrosion, resins for consolidation, or flow agents so that the powders that we're using actually flow into the fireworks that we're trying to make. And what are the products of our reaction? Well, gases for propulsion, either to shoot a shell into the air or to propel a rocket into the air. These MX chemical species I've just mentioned to make the colors. Molten sort of slag, high temperature, sticky, runny liquid byproducts from the reaction, which help propagate the explosive train from one part of a firework to the next, or solid or liquid byproducts in the flame to produce the delayed effects, or solid combustion products to produce long duration sparks. And what do we want the heat for? Well, again, gas production. Lots of gas produced at high temperature gives a thrust. Gas can also be used to produce a noise effect, and I'll show you that with a whistle later, or causing ignition of the metal or carbon particles in the flame, so we get that sparky effect, or to excite colored species in the flame. So let's think about the most simple of the compositions of all, and that's black powder. Black powder, its basic composition is potassium nitrate, sulfur, and charcoal, shown in those proportions. But its physical nature is just as important as its chemistry. In fact, its chemistry hasn't changed for hundreds of years. It's tweaked a bit now and then, but it basically comes back to that same mixture. But the form in which it's in makes a huge difference as to how it burns. That depends on the method of production, how intimate the mixture is, how closely combined are those oxidants and fuels, the particle size and the particle shape, and then how compacted it is, or alternatively, how granulated it is. And the most common black powder, I guess, we use is about the sort of consistency of coarse granulated sugar, which actually allows fire to travel between the granules as well as within the granule. So this little bit of video will just show you some different types of black powder burning. It's me quite a long time ago when I had black hair, not grey hair, so forgive me for that. But just see how different physical properties of black powder change the way that it burns.
Black powder is a mixture of three components: potassium nitrate, sulfur, and charcoal. If you mix them together, you end up with a powder in which you can still see the white, yellow, and black flakes. Now, to burn that, what happens is it goes relatively slowly. This is really quite useful for the basis of a lot of fire composition, where you want something to burn slowly enough that you can see it in the air. If it burns too quickly, it will be over and produce pointless fireworks. So lots of sparks being produced, slow burning, lots of gas, lots of smoke. And if you take that same chemical composition, you grind the potassium nitrate and the charcoal together, add the sulfur, grind it over many hours, press it into cakes, break it up, you end up with a powder of the consistency of coarse granulated sugar. Now, when we burn that, the fire can travel both through the grains and between the grains, and the whole reaction is very much more quick. This sort of thing is used for making the lifting charges of fireworks, where you want lots of gas in a short space of time. If you take the same black powder but compress it into a tube, what you get is effectively a fountain. Same composition, pressed into the tube, it only burns on the top surface.
Okay. Black powder is very powerful. It's been used obviously as a charge for weapons for a very long time, although it has disadvantages in that it produces a lot of smoke. It's very good at moving masses. And here's a very old video of just black powder showing how much force it can produce. So it's a very old piece of video, I'm afraid, of an old American conference about fireworks. But there's a charge of black powder on an anvil with a fuse. And he's going to cover it with a couple of bits of paper, which obviously make it terribly safe. And then lower on top of that another anvil. That's a heavy thing. I forget exactly what the weight is, but there was only about 25 grams of black powder there. And when it's lit, that gas has to go somewhere. And what it does is to shoot the second anvil into the air. Just look how high it goes. So that's the heaving effect of black powder. And again, that's one of the problems with dealing with explosives. Close up to them, they will move bodies, move equipment, break up manufacturing tools, and obviously therefore can be very dangerous. I'll just show you a couple more bits of black powder being burnt. This is the fountain. It's only about 7 or 8 grams. And if you put it in a tube, when the gas can't escape, all it can do is to go bang. So moving on from those simple black powder chemistry to colors, these have only really been used since the early 1900s. The color agent is not the same in the composition as it is in the flame. If you remember, our oxidant plus fuel gives product and heat. Heat excites the metal and halogen species that are partly formed from the burning of the composition and raises them to excited electronic states, which then relax to give off colored light. Think about old displays, it's really old show at 1749. It was only really gold and silver that they had, no color at all in those displays. Whereas now, of course, color is absolutely fundamental. And what is color? Well, color is what we perceive it to be. In the whole of the electromagnetic spectrum, there's a very small area of visible light between about 400 nanometers and 700 nanometers, which our eyes perceive as colored light. Sometimes trying to explain what those colors are can be quite difficult. And Newton observed, you well know, that if you pass white light through a prism, what it does is to break down the light into different colors. His experiment was even cleverer than that, because he showed that you can't then split the colors any further. And the basic quantum theory, as I said, is to take a molecule in the flame, provide it with lots of heat, which is the pyrochemical reaction, to excite the electronic state of the molecule, which then relaxes to give off a photon of light that is absolutely characteristic of that colored species in the flame. And basic quantum theory says that in bound states, there are fixed energy levels, and the light that's given off has to be the difference between those electronic energy levels, which is why we see a particular color. If it wasn't for that, it would be that we would always be producing a mess of colors, and our eye would perceive it as probably as white light. The light emitting species isn't something you can buy in a bottle. So if you think about something like copper chloride, that you buy, see it in a bottle, it's not that, it's a copper chlorine species, or quite probably a dimer or tetramer of these species in the flame, which can become excited by the heat. And if you want to maximize the amount of that colored species in the flame, the thing to do is to add lots of chlorinated compounds to the pyrochemical mixture, like PVC or saran, which is a sort of cling film. The chlorine donors enhance the color output, but of course, the more of this you add to a mixture, probably the less bright the light you're going to get out at the end, because you're diluting the original heat production. So what salts do we use? Well, to get a red, something like strontium oxalate, green barium salts, yellow sodium salts, copper salts for blue, calcium for orange. And if we are clever and the chemistry is compatible, then mixing them can produce other colors like cyan and purple. Just look at that, the yellow, sodium aluminium fluoride, which is cryolite. It seems a really odd thing to be adding to a pyrochemical mixture in order to be able to get a good yellow color, that same yellow color that you see in streetlights. But the problem is with most sodium salts is that they're hygroscopic. They absorb moisture from the air. And the very last thing that you want in a pyrochemical mixture is something that absorbs moisture from the air, because then it won't even light. And sodium aluminium fluoride or sodium oxalate as an alternative are both non-hygroscopic sodium salts, actually quite rare. And that's what's going on. Take strontium carbonate as an example. It's losing CO2. It gives strontium oxide. That can give strontium metal or strontium ions, and strontium oxide can react with hydrogen chloride in the flame. All of those reversible reactions are going on to eventually produce what you really want, which is the strontium chlorine excited species in the flame. And the problem with a lot of this chemistry is that it has the wrong chemical reactions going on. Trying to maximize the production of that excited strontium chlorine species is actually quite difficult. And so the art of the good firework maker is to be able to use both science and art in order to know what's happening in the chemical reactions to maximize that species. And as you'll recognize, they're all reversible arrows. They're all reactions that can go either way. And so that we can use something like La Chatelier's principle in order to be able to force the production of the species that we want. So let's just burn a few chemical compositions and see what the colors are that they produce. This, I'm afraid, isn't a great video, but you'll get the idea of what's able to be produced. So first of all, that is a red color. You saw it at the beginning, but actually your eye tends to turn it to white, and the camera isn't great at seeing a particularly intense color. That's what's called a lance. It's just produced. some colour over a long time. And then if I go on to a yellow, that's the yellow made with cryolite, really quite a good yellow. And then we'll move on to a green. That's made with barium carbonate. That's a decent red, strontium carbonate. And that's not a bad blue, but blue is the one to look for in any fire display. Blue is the most difficult colour to produce. And part of that's down to the fact you can see at the end of that flame, sort of yellow burning, which actually ruins it. And that's a purple, believe it or not. Again, the yellowy colour at the end of the flame burning of the paper sort of masks out that purple that we're trying to achieve. We use something called a chromaticity diagram to try and understand what's going on, because that diagram actually illustrates every possible colour that it's possible to achieve using spectral colours. And just taking the blue, which is the difficult one, when you burn a copper salt produced by this pyrochemical reaction, you get both a copper chlorine species, which is down the bottom end and a good blue, but you always get some copper hydroxy species in the flame, which tend to negate the intensity of the blue. So as I say, look out for good blue colours because they're the sign of a good firework manufacturer. So that's the basis of colour. If we were trying to produce sparks or glitter or strobe, then that's more adding metal salts, metals, and then delayed reactions using some other interesting chemistry. So the sparks are metal powders, just as I said earlier, like an angle grinder on a piece of iron. You're producing little particles of metals in the air, high temperature, they're continuing to burn in the air using atmospheric oxygen. And we can change the duration a bit by adding things like sulfides that protect the metals as they burn, but they're relatively limited in effect. The glitters are rather more interesting and complicated chemistry, where there is several reactions going on, both at the burning surface of the composition and as the particles travel through the air. And then strobes are the sort of ultimate of these three that are all related, where you get an oscillating reaction from a totally homogeneous composition. When you see the reaction, strobe reaction in a moment, it's not that there are different compositions going light and then less light and light and then less light. It's a homogeneous reaction that's carrying on, and there are lots of subchemical reactions going on there. So we'll have a look at those. Glitter, as I say, there's an on-board reaction, burning pyrotechnic composition, which is producing something which travels through the air, oxidizes away from the burning surface, and then produces a flash at the end. So there's a still of a glitter reaction. You can see there's a sort of a dark patch between where the burning surface was and where these bright effects are, where the flash reaction occurs. And it's a very attractive effect. So here's a white glitter. And that's a white glitter with a more intense flash reaction at the end. And if I light a pellet of this composition, you can see that there are sparks being produced, flashes of this light away from the burning surface. Some chemical reaction is going on with the particles that are being thrown off that chemical surface, burning surface, to produce light, and these rather attractive smoke rings as well. So there's lots of chemistry going on there, some of which is reasonably well understood, quite a lot of which is not very well understood at all. And some of these reactions are really just serendipity. Trying to make something else produces a uniquely attractive effect, and then it's used in a firework. And there's an absolutely perfect example of this strobe reaction where we've got flashing composition going off and on. And this is obviously a long duration photograph. And you can see as those stars fall through the air, flashes of light, they're not quite of equal intensity. They're not quite of equal duration. You can see that the lines aren't dots, you know, absolutely regular as they fly through the air because of all these different reactions that are going on. So let me burn a strobe for you. As I say, this is a homogeneous mixture. It's just in a little tube. And it starts to flash. Fairly regularly, fairly equal light intensity. But if I'm absolutely honest, we don't know what's going on. It's a chemical reaction that has a uniquely attractive effect in the sky, with a few problems because it burns a long time, so it could come all the way down to the ground. But this reaction is going on in a homogeneous way in that tube without really understanding what's going on. What we do know is that there are several reactions happening, whether it be a strobe or a glitter or even a long duration spark. So a bit of real chemistry here. There's an onboard reaction between potassium nitrate, sulfur and charcoal, which produces as one byproduct potassium disulfide. It reacts with oxygen to give potassium sulfide in this spritzel phase when there's very little light being produced. That eventually gets to be oxidized again to potassium sulfate, K2SO4. And at high temperatures, it's known that potassium sulfate reacts with aluminium to produce light and give aluminium oxide as a byproduct. So we know roughly what's going on, and I've been trying to arrange, not this year because for obvious reasons, but to try and trap some of those intermediate species in order to be able to understand more what the reactions are happening. Because if we understand what's happening, then we can lead to both safer and more attractive products. Well, what other effects have we got? Well, whistles, whistles, screeches, hummers, bangers, all different noise effects produced by gas. If you think about a whistle, if you blow over the top of a glass bottle with some water in it, you get a whistling sound. And exactly the same is happening when you have a composition burning in a tube. It produces a pressure wave that leaves the tube. There's a radiated wave. And as that radiated wave approaches the composition again, there's a pressure increase at the burning surface of the composition, which leads to an increase in reaction rate. And that then enhances the cycle and off it goes again. And that can produce a really piercing whistle sound. The most important effect that changes the pitch of the whistle is the length of the tube above it, a bit like an organ pipe. So here's a variable pitch whistle. Actually, in this case, we've put composition in a little brass tube so that we can alter the length of the tube above the burning surface. And you saw it's a tiny amount of composition, but produces a very shrill noise. And here's a little bit of favorite video, which I hope works, where they produced a tune by using the same composition in each of the tubes, but varying the length of the tube above the burning surface.
4, 3, 2, 1.
It's brilliant, totally impractical, but it just shows the chemistry that's going on. How do we connect all of these fireworks together? Well, we use something called pipe match normally. That's about 1 meter of pipe match in that picture. And we want things to burn to ignite almost simultaneously. So if you watch what happens when I light the end of that pipe match. That's it, it's gone. So in order to get several things igniting at the same time, in order to push them into the air at the same time, we'll either use a pipe match like this, which is effectively instantaneous, or to use electronic igniters into every firework. I'll show you a little bit about that when we come on to making displays. So that's the basic chemistry. Well, how do we turn that into compositions and fireworks? Well, first of all, the simple types of fireworks are those just with pressed composition in them. And then we'll look at some aerial fireworks with stars. So simple pressed composition, a little bit like that tiny tube I showed of black powder, pressed composition in the tube with a choke at the top, which is what's going to force the gas out and make it go higher. And it just burns regularly from the top to the bottom. These are Japanese fountains, rather a lot bigger than the one I showed you. Absolutely horrendous and dangerous, because fountains have a bit of a tendency to explode if they've been manufactured badly, much in the same way as you may recall the Space Shuttle Challenger disaster, where fire managed to break through the incomplete pressing of a composition in one of the solid rocket motor boosters, which, to be honest, are just huge fireworks, and then spread to the fuel tank and cause the disaster. There are low temperature fountains which increasingly use. These are nitrocellulose fountains, slightly different chemistry. Actually, they burn relatively cool, so I can put my fingers through them. But they're still dangerous. They're still able to produce noxious gases. They aren't the universal panacea of fireworks that some people think they are. And actually, I'm doing a lot of work at the moment looking at the use of fireworks in football stadia, where one of the biggest problems is the quantity of these things that people bring in, quite illegally in most cases, and the effects of lighting large quantities of fireworks in what is essentially an enclosed space with all the gases that are produced. In the olden days, people actually promenaded around the firework display site before the show, and they had these things called machines. So there on the left is maybe, I guess, on a barrel, but you look inside it and it's got all these different fireworks around. So they'd go around during the day and see these wonderful sculptures, and at the night, these sculptures would totally be destroyed as they fired all the fireworks. We've moved on a bit from that, although it would be very interesting, but prohibitively expensive to try and recreate that same thing now. The next level up is to produce stars, and stars are a bit like a sort of, for most cases, about a pea-sized solid lump of composition, spherical. But for the big shells and big fireworks, they actually could get up to the size of almost a golf ball with different layers of different color compositions. Obviously, they burn from the outside inward. So in this case, you might get a sort of a silvery effect turning to a gold effect, turning to a pink or a red effect in the middle. And the art of producing the most spectacular shells and most spectacular fireworks is to ensure that all the stars are burning in synchrony with one another. And that means generally you start off with a relatively small amount of composition and roll them into stars and end up with a huge quantity of stars, of which you just take the middle cut to be the most perfect and the most producing of the best effect. So what can we do with those stars? Well, you can pack them into a tube with a charge of black powder at the bottom, or we can use little whistle units like you've seen before. Very, very good for producing synchrony to music, because as soon as that lift charge is ignited electrically or by a fuse, something appears in the air. So very, very good, excuse me, for firing to live music, where you want the firework effect to appear at the same time as that downbeat in the music. And there's a typical set of mines being fired across a front. The next step up from that is sort of multiple effects. So a Roman candle has anywhere up to 10 or even more of these little units inside them, and might last over 45 seconds. You see on the left of the screen Roman candles being used. They are great for adding continuity to a display, even with music, where you then pick out the highlights of the music with aerial fireworks bursting over the top of them. So there, Typical display at the bottom of the screen, Roman candles going off. These ones happen to be candles that split when they reach the apex of their flight, and then above them, the shells, the most spectacular fireworks of all, bursting over the top. Rockets, funnily enough, are not used very much in professional shows, mostly because they're relatively unpredictable in flight. They tend to head into the wind because the stick is blown backwards. But worse, that this stick and the head must come back down to the ground. Whereas most fireworks almost self-destruct when they've completed their effect by being blown apart as the stars are lit and the casing is ruptured. In this case, a rocket stick must come back down again, and that obviously can create problems. The Americans always go better than us, and so they put firework rockets on the bottom of this sort of portaloo. But they also do all sorts of strange other things, some of which are successful, some of which are definitely not successful. But the ultimate in the fireworks that we use for displays are the shells. This is just like an artillery shell, fired out of a tube called a mortar, mostly spherical, but there are some cylindrical ones as well. And inside the spherical part of the shell are all the stars arranged in a particular pattern to produce the effect that we want in the sky. At the bottom of the shell, there's a lifting charge. The lifting charge is black powder, and when you ignite the shell, the lifting charge is ignited, and that yellow delay fuse is ignited. The lifting charge propels the shell into the air, and it leaves the tube at roughly 400 miles an hour, so there's a lot of oomph behind it, and can go anywhere up to 1,000 feet in the air. The delay fuse burns to produce the burst of the shell. The bursting charge in the middle of the shell both ignites and fractures the case, and that's what you want to happen at the apex of its flight. There are some big ones. There's a cylinder shell made typically in Malta or Italy, and increasingly there have been some in America, but the Americans always go a little bit bigger than everybody else, and that might be a repeating shell with lots of 7 or 8 different effects in it, one after the other. But they also make much bigger ones, up to 14 break, and I've seen those actually come back down to earth before the last break has gone. So again, what goes up will come down, and there's a trend obviously to try and ensure that what comes down is the least environmentally sensitive and the most safe, and that isn't. These are how the shells are made, paper hemispheres with stars packed all around the circumference of that sphere. Then they're filled up with the bursting charge in the middle, and then covered in layer upon layer upon layer of paper to try and make sure that the shell is symmetrically strong, if you like, that it doesn't have a weak point when it bursts, so that the effect in the sky is also a spherical burst. In the Far East, they dry all of these things outdoors. They have the weather for it, but if you have an accident, of course, the fire will spread dramatically and quickly throughout that lot. And they've had some horrendous accidents over there where they've been drying material outdoors. We don't have that problem in the UK because the weather's not that good. And this is a 48-inch shell being lowered into a mortar, a huge shell. Actually, not worth it, to be honest. It's so expensive and so dangerous, and the effect really isn't as good as you'd expect it to be. 12-inch diameter is probably the sort of optimum. It's the highest and the most regular in its burst and carries the most material while still being both affordable and safe. Some shells are lit on water. Here's a show again in Japan. So you can see half the burst because the other half of the burst is underwater. But you can see those craft in front of it, holding other fireworks, they're barges. So you get an idea of the scale of these things. So there are all the firework types that we tend to use. Now let's turn them into displays. We have to know how high the fireworks will go, what the trajectory is, where they'll burst, where will the debris fall, and where would an unfired shell fall if there's an accident. We also want to design the show. So safety and design, the art, have to go hand in hand to make sure that what is produced is both safe and spectacular. On the safety side, we've developed over the years a program to model where the debris goes, and this is used now all over the world in order to be able to plan safe shows. And we superimpose it onto maps in order to see where the debris would fall. That's for London New Year's Eve in previous years, where the debris obviously we want it to fall in the river, but we have to see where it's going to fall in all sorts of different wind conditions. And then we plan as to what's available or not available. And we come up with what disparagingly is called my refreshers diagram. For those of you who remember terrible sort of sickly sweets that were green, yellow, and pink. So the green things are things that we say is good and can continue. When it becomes yellow or orange with different wind speeds and different wind directions, then we have to start thinking about removing material from the show. And when it gets to red, then the show may even have to be cancelled. So we try and come up with a objective set of curtailment or cancellation criteria before the show ever starts. Once you're into the show, it's obviously much more difficult. So a few displays. Well, this is Plymouth in the UK, the largest annual firework competition in the UK. 6 competitors set up, and there you see rack upon rack upon rack of shells being loaded for this show. And if you get the chance, it's really worth seeing. 3 shows a night, 2 nights, and spectacular displays because everybody's trying to win the prizes. It's on a breakwater, so everybody who sees it gets the view not only of the fireworks but of the reflections. Water is great when you're dealing with fireworks because the effect can look so much better. And they go up to quite big size tubes as well. So here's the result. And you can see even from a relatively small firing area, you can get a really spectacular, both high and wide effect. And again, look at the size of the boats in the foreground and you'll get an idea as to how large these fireworks are. Again, there's the strobe effect. And again, you can see how wide that can get. And there are Roman candles to produce this continuous lower level effects, which as I said when we mentioned the Roman candles before, could last up to 45 seconds and give you that base level effect before you punctuate it with big shells over the top. I was involved, or I designed the Hong Kong handover show in 1997. And there you see, an enormous quantity of mortars on these barges in Hong Kong. We had several barges. It was the most horrendous weather. We had 17 inches of rain during the setup and 5 inches of rain on the night of the show itself. But these things are so powerful, what you do is to cover them in tin foil and plastic, and they're so powerful that the shells just burst straight through that. So we can keep them waterproof, and still the show will go on. Very young me and a lot of the other crew for that show. And this is the end result. Again, look at the size of the barges. Those are 12-inch diameter shells bursting at the top. In the UK that year, I think we only used 3 or 4 throughout the whole of the year, but we used 57 of them in that show on its own, because Hong Kong, if you know it, is a grand harbour, people watching from all around and from quite a long way away too. You have to have something that is truly spectacular while still being safe. There again, more of these effects off 3 barges. And this one, it did just about clear for the show itself, but you can see the low cloud up there. And hopefully that proves it was actually in Hong Kong. Just a couple more. VJ Day in London. There were 5 barges all along the Thames. I felt really sorry for the guy that was photographing from this place because the smoke was heading in his direction. And that's about the only decent shot he got. But trying to coordinate 5 barges firing the same things together is obviously not trivial. Somewhat easier now with computerized firing systems that exist. And that's right down at Tower Bridge. And you can see HMS Belfast and another boat moored alongside it, and using the full width of the river in order to produce the spectacular show that it was. Malta, I did a documentary in Malta a few years ago, and here's a little guy, 3 Maltese firework men, one with a firework on his shoulder, the guy standing up with the mortar in a barrel full of sand, and they reload their fireworks when they fire a show. If you think back to the Hong Kong show, we had a unique tube for every shell that was fired. So as many tubes as we had fireworks, but here they reload them. And how they do it is this guy runs from a van with a firework on his shoulder, and the little guy in the middle has a cigarette behind his ear. And once that shell's popped in the tube, he lights it, and all 3 of them run away until they light the next one. Quite frightening. Those are more of the tubes, but they only had 6 tubes for the whole show, and there were probably 300 or 400 shells. They're also a bit cavalier. These are rockets in that frame, hundreds of rockets fired together. You light one, and the fire from one lights all the others, and they produce a fantastic sort of sheath of corn type effect in the sky. The mortars there for firing bigger shells, well, somebody's told them they ought to put a few sandbags down to hold it up, but it's a bit cavalier, really. And sadly, many of the accidents that have occurred in Europe have been, you know, this sort of type of thing where adequate safety precautions have not been taken. Athens Olympics 2004, I was involved in, firing off the roof and the arches over the stadium. Really spectacular show. But the types of fireworks that you can use are obviously very restricted when you're firing directly off structures, when you've got people underneath. So special low debris fireworks that are not going too high and are not spreading their debris on the ground. And then Melbourne 2006 Commonwealth Games, working on a glass roof, which poses its own challenges, as you can well imagine. Firing systems now all electronic, basically all pre-programmed. Every firework has its own electric ignition system, and you just eventually push go on the laptop and the whole show fires itself in time, in synchrony with the music. Much, much more precise than ever we could have achieved before, but in some ways lost some of the drama. And that's what you end up with. This is the stadium in Melbourne cricket ground. Mines fired off the rim of the stadium, but what we had to be very careful of course, is to make sure that no debris falls on the athletes who are in the middle of the stadium at the opening ceremony, because frankly, you know, falling a piece of debris onto an athlete at the beginning of the Commonwealth Games is not a great idea. Probably at the end of the Commonwealth Games you might get away with it, but obviously not something to aim for. And it was a unique show, and really one of the first to try and encompass the whole of the city in the display. So that's the Yarra River running along through Melbourne cricket ground at the back to fire most of the show from, and then a synchronous show fired off the rooftops of the tall buildings. And it was the beginning of the modern sort of design of shows, where the show was punctuated with elements that were happening in the stadium. Not a continuous firework display, but a very choreographed one. Problems again, because they wanted fireworks on the performers in the middle of the stadium, and came up with this idea of having fountains on their back or wheels on their back, all remotely triggered. And just to add spice to it, all of those performers were on roller skates. So everything making life very difficult, really. And then lastly, really about New Year's Eve, London New Year's Eve, obviously not this year, but in previous years, using the London Eye. It's a great structure for firing off, but the Thames isn't a great place to watch a firework display because so few people can actually get to the area to see it square on like that. The Eye gives us lots of possibilities, and then enhanced with barges to fire aerial effects to synchronize with what's going on the Eye itself. So very spectacular. The future, well, what's the future for fireworks? Well, there are obviously the concerns that we have, the environmental concerns, the safety concerns, and there will be novel compositions in the future based on high nitrogen organic chemistry, I suspect, but they're expensive. And we can't make a shell, couldn't make a shell in the UK for less than about £12, while we were buying one from the Far East for about 50p. So there's always got to be a playoff. They are not high value items. There'll be less environmental effects, both from the chemistry and from the debris, more monitoring of that, of course. Greater precision, we're now down to sort of hundredths of a second, but when you're firing a big chase off the Eye, or take Sydney Harbour Bridge, you want the precision to be absolutely there in order to be able to get this run of effects across the structure. So that will lead to more sophisticated firing systems. And inevitably, whatever happens, there'll be more regulation. As I said, the second most regulated industry in the UK after the nuclear industry, but it'll just get worse, I'm afraid. So just a few thank yous. These are the people I've worked with in recent years, all who've produced photographs for me or given me advice, helped me with the book, all sorts of things. And there's some details of me. Very happy after today. If you think of something that you'd like to ask, drop me an email or have a look at one of those websites where there's a lot of information. So thank you very much. Mark, back to you.
Excellent. Well, thank you very much, Tom, for that that excellent talk, and very impressive photographs, videos, and the chemistry behind it as well. So thank you so much. Tom has very kindly agreed to take a few questions as well. So we have some in the chat that we will start with, but if you think of any, now's your time. Please put them in the chat. So I'll start off with, actually, there's a bit of chemistry first of all. Someone was wondering at the very beginning of your talk, why was the water needed in the reaction between the silver nitrate and magnesium at the beginning? So
Okay.
what role did the water play?
Well, the water was helping dissolve the silver nitrate, which made it possible then to react with the metal species. It's a sensitive composition, but as long as you keep it dry, then that reaction can't occur. But as soon as you add any moisture to it, then a little bit of dissolving, a little bit of nitrate, probably a little acidic, and the reaction proceeds like that.
Excellent, thank you. And in fact, when you mentioned the future, you mentioned sort of making fireworks more environmentally friendly. So someone's actually asked, how can you do that? What sort of things would you consider to make fireworks more environmentally friendly? So things like less waste falling to earth, etc. What sort of things are being looked at?
Well, there's been quite a change in the construction of the fireworks. So many more now are using paper in their construction, or card, so it rots down quicker. In fact, those hemispheres that you saw in the construction of a shell, in let's say 20 years ago, everybody was making them out of plastic because it produces a better effect. But then bits of plastic fall to the ground, which don't decay for tens of years. And there's quite a lot of work going on actually in injection molded starch, which will produce a very rigid construction of the shell components. But first time it rains, they all go to mush and all disappear into the ground without a problem. On the chemical side, well, there is work being done. It's expensive. It's not going to be in place for, I wouldn't think, 10 or 20 years. But I have to caveat all that with, actually, like the London display, if the chemical byproducts of the reactions are only 1/300th of that getting people to come and watch it, are we concentrating on the wrong things? We still need to be entertained. We do lots of other things that use cars and buses and trains and tubes. If it's only 1/300th of the amount of SO2 and NO2 that's being produced, I think that's pretty good, actually.
That's very true. It's interesting to put it into perspective when you quote those figures. Yeah. Couple of related questions actually about the noise. So you show videos of the whistler going off. Someone's asking, would you classify the noise as part of firework as an unwanted product, or is it something that's desirable in a firework?
Well, it's very definitely some and some. You know, if I were firing a show for a primary school, I wouldn't have a noisy display. If I was firing a show where there were known issues of animals or an old people's home or whatever, yeah, I'd try and keep the sound down. But at other shows, you know, it's perfectly appropriate and is another one of those stimuli. You see things, you hear things, you probably smell things as well. There is no such thing as a silent firework display. Whatever anybody says, if you're going to have a burst of stars in the sky, something has got to burst the shell, and that's going to produce some noise. But it's the right thing in the right place at the right time, and let people know. Even animals, we find with horses, which are skittish animals, if there's a stable nearby and they play music to the horses in the stable, to break that time between silence and noise, then the animals are pretty good. And we find that in wild animals too. You know, we did a show over a lake, and the first shell that went off, all the birds flew up off the lake. But halfway through the show, they were all back again. It's that break between silence and noise, which is the thing that affects them. In the same way, if you took a shotgun out there and fired it, they'd all take flight at the same time anyway.
Excellent. Yeah, thank you.
I've got a couple of questions too, Matt. So one from Lily. She asks, what was the worst thing to go wrong during a performance during your career, Tom?
Well, look, I've still got 10 fingers and thumbs, so I'm okay. When we used to fire the big shows on the Thames, we hand fired them, and I've had the odd occasion where a shell has just sort of popped out of a tube and fallen down onto the barge that we were on and then gone off. But actually, like so many things, I think time seems to stand still at that point, and it seems like ages, and you can turn around and shield from it. There have been stories of shows, some of them apocryphal, but some are true, where they've used a firing system and something's gone wrong, or they've left it on a sort of practice mode and they push the button and a 20-minute show's been fired in 20 seconds. And I think that would be pretty mortifying. Very spectacular, but pretty mortifying.
I've got one other question here. What's the largest firework that you've worked on or worked with, perhaps?
I've really only gone up to sort of 12 and 16 shells in the UK. As I say, they're horrendously expensive, and actually the effect isn't great. But I have been in Japan with crews when they fired 24-inch and 36-inch shell. But you know, those huge shells are probably costing as much as the whole of the London New Year's Eve show in one 3-second shell. So not used very often.
Fair enough. Thank you. Another one's just come in as well from Hirkesh. How is the height of a firework controlled?
Well, for the shells that we use, there are two factors really. One is the size of the shell. So bigger shells tend to go higher. It's roughly 100 foot per inch of shell diameter. So a 4-inch shell goes to 400 feet, and a 6-inch shell goes to 600 feet. But you can also affect it by the amount of lifting charge that you've got and the length of the mortar tube, just like a gun. A longer shotgun fires further than a pistol. So if you want a very precise effect in the sky, you can make these shells specifically so that they might burst in a circle by very clever production techniques, very careful weighing and simultaneous ignition. So we can now get a sort of a 3D effect as well as just sort of a vertical or a horizontal effect.
There's one here that's quite interesting. Someone has actually asked, how does one become a professional fireworks engineer stroke designer?
Well, it's not a huge industry in the UK, as you can well imagine, although actually the pyrotechnic industry more generally is quite well established in the UK. So an interest in it, chemistry is always good, and the companies that fire these shows, not in 2020 for very obvious reasons, but in any other year, are often looking for people to come and learn the art in their local area. So just scout around, see who's around, approach them, and if you don't appear to them to be a liability, I'm sure they would be very glad to introduce you to the art and train you up, and then become a firer with them in the future.
Excellent. And someone's asking for your personal opinion and asking where you stand on the debate over whether or not fireworks should be used at public displays only.
Well, I don't expect it will surprise anybody to say I don't think that domestic consumer fireworks should be banned, but I don't do that on any sort of silly subjective grounds. The evidence that we have across Europe, for instance, is that the countries that have banned fireworks have actually ended up with more accidents and more distress than we've got in the UK. It's very, very well controlled in the UK. Just to give you an example, Berlin on one night, when they're allowed to use fireworks, again, not this year, is New Year's Eve. And there are more accidents, more hospitalized accidents in Berlin on one night than there are in the whole of the UK in a year. Just one city exceeds what the whole of the UK is. And that's because New Year's a rotten time of year to fire fireworks. The weather's bad, people have probably taken too much alcohol. All the things are against it being safe. Careful management, proper fireworks that meet the standards that are around European standards, and critically, if people read and obey the instructions on the sign. I think too often, probably Brits feel they know how they should do these things, and it's a dangerous product. You've got to treat it in the same way as other dangerous products. And so, as I say, the mantra really is the right thing in the right place at the right time, and let people know, whether that be a private individual who's got a neighbour with kids or dogs, or a big display where there's other potential problems around hospitals, other people's homes, whatever. Letting people know. In most cases, if they knew about it, they'd come out and watch it and it would be great. If they don't know about it and they've gone to bed, then it can be upsetting.
Excellent, thank you. I think just interest of time, just a couple more questions, but what's quite interesting is when I was asking you, how do the computer-controlled fireworks work?
Okay, well, instead of there being a fuse, and I showed you that quick match burning, which would be a manual ignition, every individual firework would have an electronic or electric ignition. So a little device that's put into the fuse in the shell, right into the lifting charge of the shell perhaps, and then lead the wires back to a firing system. Now, for the Hong Kong show that I showed you pictures of, we actually had 18 miles of wire between the different fireworks in order to be able to fire that show correctly. But modern systems have gone a level beyond that, with the computer-controlled systems with remote boxes where a signal is fed and then it's an ignition is triggered from these remote boxes. So you can get down to this 10 millisecond type of accuracy that is so important when you want to produce that spread of stars across a structure like, as I say, Sydney Harbour Bridge or something like that. What it has done, of course, is to put the price up, because for every individual firework, you've got to have an individual igniter. And sometimes I think we lose sight of the fact that people would sometimes in smaller shows rather see more fireworks than to know it was lit electrically.
That's excellent. And in terms of shows in the future, someone's asked quite an interesting question about how will the regulations change when we leave the EU?
Pass, I don't know. We're only a month away and I don't know. But the UK, nothing much will change in the UK. Most of the stuff that we use in the UK is imported from the Far East or some from Europe. And you don't do something like VJ Day with only a day's notice. It takes a year to plan an event like that, so you've got time to bring the stuff in.
Excellent. Do you have any further questions, Steve, on your feed?
No, that's all of them now. Thank you.
Great. Well, in the interest of time, I'd like to say thank you very much to Tom for giving up his time and giving us such an excellent and informative talk. It's obviously such a shame we couldn't be in the lecture theatre, where I know Tom does a lot of this on that wooden bench at the front, and the noise and the smoke it hits all the senses. It's fantastic. But thank you for at least giving us some insight with the videos there. So I want to join and say thank you so much for such an excellent talk, and we just wish you all the very best in the future, and to see some fireworks again soon as well. So thank you very much, Tom.
Thanks, Mark. Thanks, Steve.
Yes, thank you.